Hello there, everybody, and welcome. We are going to continue on with our lectures. Our next topic is phase equilibria. So let me go ahead and turn off the video, share screen, and let's do it. Share screen, go to this. All right, it should be good. All right, so phase equilibria. We've just come out of talking about the Gibbs free energy and Helmholtz free energy. Now we're going to start to apply equilibrium, free energy processes to some certain applications. And these are going to include things such as, hopefully I can pull this out so I can, yeah, the Zoom meeting things are covering my pens. Can I close these? I don't know how to make that go down. All right. So what I want to do is talk to you about phase equilibrium, right? So phase equilibria is an equilibrium concept, and this has to do with free energy because we're talking about what will happen. And so one of the things you might want to know is which phase are we going to be in? Phase equilibria. So many substances exist in solid, liquid, and gas, which is the way we oftentimes talk about the phase equilibria. But also some of the things that we may be interested in have to do with, let me try minimizing this. Sorry, this keeps blocking my view. I can't write here because it's menus in the way. All right. All right, so what we want to see usually is that substances like water are going to exist in solid, 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 liquid, and gas. There are also other kinds of phase transitions that could happen, such as we see with lipids, which is pretty complicated. But a lot of the principles that we can see with just the normal familiar solid, liquid, gas are going to apply for many of these things. So this is going to be modulated by temperature and pressure, right? So at different temperatures and pressures, then things are going to be at a different phase. So we're pretty familiar with that. We're watching the temperature all the time. Right now it's winter time when I'm recording this. Just had a snowstorm this past week. There's snow on the ground, so we're all thinking about snow and ice, water in the solid phase, and steam is, of course, liquid in the gas phase. So we all know that when we change the temperature, that the phase of water could change. But it's also true for many other things, and the phases of biomolecules could be really quite important. There can be transitions between different phases. So like, for example, the beta amyloid proteins that can form plaques in the brains that may have something to do with Alzheimer's disease. Seeing how these things change their phase from the soluble form to the not soluble form. Could this be temperature dependent? How do liquids that have various salts in them change when they're going to undergo phase transitions? This also is something on our mind as we may be putting down salts when there's ice outside. Could it be too cold to salt? How come they don't use these in very, very cold climates? We'll talk about some of these things. So the phases are in equilibrium. Along the boundaries in the phase diagram. We'll be seeing some phase diagram shortly. Various temperatures and pressures. And the states of the substances are going to be presented in a phase diagram. Which phase exists under specific conditions is dictated by the Gibbs free energy. By the Gibbs free energy. Remember that we have delta G equals delta H minus T delta S. So for example, this T right here is the operative thing that tells us what state things are going to be in. I really wish there were a way to hide this Zoom menu. It usually auto hides for me, but now we have all these windows blocking up my space. I can't like move the pens for some reason. I can't change my pens. I don't know if you can see all the Zoom windows, but they are blocking my view. It's very annoying. Okay. Anyways, we will examine phase transitions. And today we will look at phase transitions. And we'll see a little bit about the chemical potential and the chemical potential related to the partition function Q, which you might remember we met in the chemical statistical mechanics view of all of this material. All right, so let's take a look at phase diagrams. So a typical phase diagram might look something like this. Okay, so here's the pressure. This one happens to be in torrs, and we have 100, and we have 0, and we might have something like this. And then we have something, okay, so this is going up to 320. This is temperature in Kelvin. Here we are down at 250 to 300, and here is 285. And we're gonna have, so I am picking out some points here. So it's got a little bit of a tilt to it. Okay, this is the solid phase. And so here is the gas phase. And so as you might guess, this here is the liquid phase, right? So this covers the area up into the boundaries that I've just drawn. All right, so this is this benzene. Okay, So then we can talk about the various things that might happen between the phases. So what is it called when you go between a solid and a liquid? Right, well, that's melting, right? So this is the melting line. And to go between a liquid and a gas, that's called vaporization. And to go between a solid and a gas, this is called sublimation. Sometimes in the winter you can catch some snow on a roof, particularly of something that's not heated underneath, like a garage. And when the sun comes out, you might actually see the vapor going right off. The snow's not really going in between into the melting. It's going right from solid to liquid to gas. All right, so we may want some points to talk about on the phase diagram. So point A is clearly well within the solid range. Point B here is within the gas. C is the point down here, right on the sublimation line. D is a point on the vaporization line, and E, where is E on my picture? I don't see an E, so I'm going to hold off on that. And this right here is point F, this one right here. So we see their coexistence curves. Between the phases. We have the sublimation, the vaporization, and the melting line. The phase diagram shows what happens under P and T at the various phases of solid, liquid, and gas. So notice those are the axes, pressure and temperature. Liquid and gas exists. And a point on the diagram corresponds to some particular P and T. So you just read it off the axes and shows the phase. All right, great. Curves show temperature and pressure. In which multiple phases exist. Such as these lines here, that's the boundaries. So in this picture, line segment CF specifies solid to gas. The boundary between solid and gas, let's see. It's not really two, it's really solid and gas. Solid gas boundary, right? Then we have the FA. Now, let's see. FD would make more sense. It's the vaporization. solid to gas, which is the sublimation process. FD is for the solid to liquid. And that process is called melting. And we also have the liquid gas, which is on FD is that solid to liquid. FD, not really, that's liquid to gas. This is, all right, I don't know, this is must supposed to be E here. Solid to liquid, let's make sure we get it right. Solid to liquid is melting, but it's not D, it's E. FE, and then we can go along the line segment FD, this one. FD is liquid to gas. And this is called vaporization. All right. All the pertinent features may not be conveniently fit on a phase diagram because the pressure scale spans a wide range of values. And so oftentimes you might see this as a semi-log plot. So when we see such plot in semi-log or log space. So just pay attention to your axes. And the semi-log version. Critical point. So let's just take this and let's do a semi-log version. And then we would get something like this. Which will look more like we have solid. It's just a transformation is all it is, right? It will look more like that. So this would be log P towards, this would be about 5. This would be about maybe more like here would be 1, and this would be about -1. And here we have our point C again, and we have various points of interest that we might wish to discuss. So this is at 1 atmosphere of pressure equals 1 atmosphere. All right, down here is temperature in Kelvin. So this is why we might have a log version, because it might be more convenient to look at it. So there now we have the semi-log version. And the critical point, let's just take a look at the picture where the critical point is. The critical point is this here point F. At the critical point, this is the phase at which the liquid gas phases are not distinguishable. Basically, it means you're in the fog. experienced this at the ocean once. It was very strange. The whole air was just like fog, and you couldn't see anything. I mean, a foot in front of you, you couldn't tell. It was really weird. You get lost in a place you knew well. The point, of course, the critical point is that this is at all points on the graph, but the point at which the liquid gas phase phases are no longer distinguishable. Between liquid and gas without a proper phase change. Like boiling water, that fog that can develop on the top of the water. It's whole one because solid liquid phases. Okay, solid liquid are going to be more distinct with sharper difference. This is the loss of intermolecular interactions. Both are anytime you have a phase change. So as you go from solid to liquid, liquid to gas, you're losing those intermolecular interactions. The enthalpy is decreasing because you do not have, well, the magnitude of the enthalpy is decreasing. So it's becoming more plus. And of course, when I'm discussing the fog on the beach, this is at 1 ATM. So you could walk along that point at various other pressures. So for solid to liquid, there is no equivalence to the critical point. We talk about the critical point, but this is what I mean because they think about this at a particular pressure, but there's actually the whole line at the border between the two of them. So what you do is you read across the horizontal line. Corresponding to the of interest. So usually it's 1 ATM for those of us who live on Earth. So for example, this might be equivalent to 1 atmosphere equivalence in torrs. And so here is the boundary between the solid and liquid. As we go over here, this is the boundary between the liquid and the gas, right? So that critical point that we're talking about would be right here, right, where you get that fog. And here's where you would get the melting. But if we were at a different pressure, then it would happen in another point, right? So the critical point would be moved. And as you can see, as you have as you change the pressure, then that situation would be different according to that curve. Okay. So in other words, you just read vertically to see what will happen with the right. Why does ice melt under pressure? In other words, why do ice skates work? Why does ice melt under pressure? All right, so let's take a look at our graph for what is ice skating work. So just in case you weren't aware, when somebody is going ice skating, the reason why the skates glide across the ice is because the ice is slippery. But the other reason is because the blade of the skate concentrates the weight of the person into a very small area. And by pushing on the ice, it's going to locally melt to make a little bit of water. And as you know, ice with a little bit of water on top is way more slippery even than just regular ice. And that is essentially that. But why is it melting in the first place? All right, so let's look at another graph. Here, so we got the log pressure and the temperature here. And we're gonna have, it looks like a Y. Okay, this is the solid phase, the liquid phase, and this is the gas phase. All right, and here's the temperature. Now, put a dot right here and go whoop, like that. So this is a water diagram. And let's look at a typical normal phase diagram, which would look something more like this. Normal phase diagram. Original data. Measured it myself. Yeah. Sketch, obviously. All right. So right off the bat, one of the things we notice is that water, once again, is unusual in some interesting ways. So notice that the slope of this phase diagram is not the same as the slope over here. Right? This is a positive slope. This is a negative slope. And here's the temperature down here. So, well, that's interesting. So let's just make note of that. The slope is negative, whereas this slope is positive. So what is the implications of that? Who cares, and how did that get to be that way? All right. Consider the slope of a solid liquid phase boundary. Looks interesting. This is melting. The slope is plus. as is for normal substances. This is normal. An increase in pressure goes into S phase. Or, in other words, there's no melting. If the slope is negative, as it is for water, the increase in pressure goes into the liquid phase. And we get melting. So let's take a look. So here we have the water phase diagram. Here's the regular one. So if you increase the pressure, right, going up here, if you're at some point, say this is like, 1 atmosphere. Imagine that's 1 atmosphere and you put pressure on it, and so that you're moving up in the point here. You're going to be more in the solids. So you're not going to have more melting. You're going to have more melting as you cross this boundary into the liquids. But because the slope of this phase diagram is unusual for water, as you have some pressure being added, such as you stand on an ice skate and concentrate all your weight on 1 blade or 2 blades of an ice skate, you're going to locally increase the pressure. And as you locally increase the pressure, it goes into the liquid phase. And this is why ice melts underneath the skate and makes it more slippery and makes ice skating work really well. It's very slippery. Any ice skaters out there? Need to turn the light on, it's getting dark. So just an FYI, I've exaggerated these plots quite a lot, so real ones probably aren't mostly gonna look that dramatic. But you get the idea, and I just drawn you a schematic so you can get that point. So let's just explain how ice skating works. So when someone is ice skating, they causes a local increase in pressure. This causes the ice to melt. But you also see those lines after people have been skating on the ice. Doesn't look beautiful and clean as it does after it just gets maintained. This becomes more slippery. To the water on top of the ice. And that's how skating works. No. It gives free energy. All right. The gives free energy of a substance has a close connection to its phase diagram. It is diagram. Consider the plot of delta G Gibbs free energy versus T. So in other words, we're thinking about dg dt of T equals S substate. That's what we're thinking about. All right, so this is going to be molar, so that's why there will be a line on top. That means it's molar. Remember that. Just so we remember. So we're going to have something like this. And we're going to have something like that. Here's solid. And here's liquid. And there's a point in here. And we might have a line of demarcation here. This is temperature in kelvins. This here is the point of intersection. Curve is continuous, but the derivative is discontinuous. T-N-U-O-U-S. Remember that when you have a point like this, where you could actually have multiple ways of aligning your tangent line, that's considered to be a discontinuity in calculus, because there's not a unique way to place the tangent line. Whereas if you have a round curve, there's a unique way to be perpendicular to it. So in other words, this over here is a steeper slope. And this right here has a discontinuity. Derivative discontinuity. Right. So imagine walking along this line. When walking along the G molar Gibbs free energy versus T line, the system will move through the lower G when a choice is available. Okay, so what exactly do we mean by that? Notice this line right here, we could walk along this and we could keep going along this line here, right? But now in this region here, we have a choice of which way it could go. And so because of that, this is what we mean. We have a choice which line you want to walk on. At the point of intersection, which is this right here. At the point of intersection, the system will switch with a lower curve. Because it's a lower G. Remember we talked about that already? We talked about how Helmholtz and Gibbs free energy are trying to go to a minimum, whereas the entropy is trying to go to a maximum. So it will choose. You have choice. It will go to the lower one, which is more stable. And this results in a phase change. So that is the driving thing behind that. All right, now let's talk about the chemical potential of a substance in a phase, in two phases in equilibrium. All right, so let's just understand exactly what we are thinking about here. So I'm going to draw another one of my pictures. I have another cylinder. I have a lot of cylinders in this class. And we're going to have some wheels on top. All right. And here I'm going to color this with a marker. There's going to be some nice liquid in here. Okay, and also we have a cover on this. This is a lid. Alright, it's closed and it's clamped shut. Okay. Wouldn't really work if the gas was open to the air above the experiment we're going to talk about. Okay. Constant P and P. Okay. So now what we want to consider is the Gibbs free energy in the two phases. So as you might guess. Space. This is the liquid phase. Liquid phase. Okay, and we might even think about like some molecules. So I'm not going to draw every single molecule, but we're thinking about the idea that some of the molecules in the liquid might be coming up and some of them are going back into solution. Maybe they're waters, right? And there's some of them coming up and there's some going back down. Ooh, there's one way up there, right? And so there's lots of molecules up here. So I'm not going to draw every single bar. You get the idea. A small number of molecules. Transition between phases. All right, so let's understand about the total Gibbs free energy in the system and what it has to do with the different states. The total Gibbs free energy is the sum of liquid and gas phases. Of course, it will be a sum of whatever phases you have. That's the phases that we have here. So G total equals the Gibbs free energy of the liquid plus the Gibbs free energy of the gas. Consider a system consisting of two phases. A pure substance in equilibrium with each other. For example, water vapor and liquid water. Total Gibbs free energy is then given by the sum of the energies in each phase, as we just wrote up there. Total Gibbs free energy total and is given by the sum of the energies in each phase. Right, this is why I have GL plus GT, liquid and gas. Now let's consider that some small number of molecules are transferred from the liquid phase to the gas phase at constant temperature and pressure. So that's why we wrote constant temperature and pressure. If you change the temperature or you change the pressure, that's cheating. But this is about what's happening inside of here. Okay. Now, consider some small number of molecules in N moles are transferred from liquid to gas. So some of the molecules in the liquid go up to the gas at constant P, of course. And the decimal change in the Gibbs free energy is given by up. G change in Gibbs free energy in the gas over the number of molecules in gas at constant pressure and temperature plus Ag liquid over the number of molecules. DNL. This is G for gas, and that's for liquid. DNL. Sorry, I forgot. DNG goes here. Right, so it's saying the change is going to be about the infinitesimal change of one. So in other words, as some molecules go up, in order to keep things in equilibrium, some molecules also need to go down so that it stays equal, or else it's not in equilibrium. So note, however, the amount lost from liquid is equal to the amount gained by gas. This is due to a closed system. So in other words, D and change in molecules of the gas is equal to the positive DNL. This is what keeps it in equilibrium. So if you add some to the gas, there'll be an equal amount from the liquid that will go to the gas. So they, however many come up, also need to go down. So we can sub this information into our partial equation up here. So sub in and factor. So when we do that, we get G equals dg T dng P comma T minus G over dn net D in liquid P comma T dn G. So this happens because of the chemical potential. So U, G, and U, L are the symbols. Chemical potential. This is the tendency to undergo a phase change to return the system to equilibrium. So if some gases go up into, so if some liquid molecules go up into the gas phase, now there's more in the gas phase than there were before. So this chemical potential will develop, which will be the tendency of some of the ones in the gas phase to go back to the liquid phase to replace the ones that left. It's analogous to electron potential with charges, which measures the potential of a particle to move to equalize the charges. By the way, all right, so writing dg needs to be a capital. dg in terms, excuse me, chemical potential. U. G gas minus du of the liquid with respect to the number of particles in the gas at constant temperature and pressure. What is the interpretation of this? If two phases are in equilibrium, then the delta G equals 0. So there's no and G equals UL. I'm writing the superscription. I switched there for some reason. Okay. So in other words, the chemical potentials balance each other out, so they're equal. So dNg is not necessarily equal to 0. It's just because the molecules may be crossing the phase barrier, but they're doing so in equal numbers. So this means they're interchanging, but they're interchanging in exactly the same amount so that we maintain the pressure on either side. If two phases are not in equilibrium, then a spontaneous transfer of matter from one phase to the other will occur. One phase and the other will occur such that dg is less than 0, right? Goes in the negative direction. dg wants to be more negative. Suppose, let's consider, for example, suppose some gas particles transfer to liquid. Now there's too many in liquid. So in other words, do what is spontaneous, which is to undo whatever caused the imbalance in the equilibrium. So if UG greater than UL, then let's take a look at what's happening. DG negative equals UG minus UL dN for gas. So this term is plus, this term is minus. So let's just understand this. So it's negative to do a spontaneous change. It's plus that. UG is greater than UL because we said that we are transferring gas to liquid. Therefore, in order for dg to be negative, this term must be negative. But this one's positive and this one overall is negative, then this one's got to be negative. Must be negative. So we can capture this explanation like so. dng must be plus, must be minus, since we know dg is less than 0. Mass will transfer from the gas to liquid. And matter will transfer from phase with the higher chemical potential to the phase lower chemical potential. Makes sense, right? All right. And in the last few minutes, we will talk about the Clausius-Clapeyron equation. APE Y equation, which gives the vapor pressure of a substance as a function of T. Right. You can use this if you know any 2 points, Pt and the molar vaporization enthalpy, delta H, which is table value. Say any one of these numbers may be unknown. So in other words, you need a total 2 of 3 out of these things. So you have 2 points and heat of vaporization. So if you know 2 points, the PV, the PT points, then you can solve for the vaporization. And if you know the vaporization 1 point, you can solve for the other point. It does not, however, take into account the change in volume. Does not account change in volume from liquid to gas. But it's a pretty good approximation and assumes ideal gas, which not all of them are, but nevertheless, it's a useful equation. Ln P2 over P1 equals negative delta H bar of vaporization, molar vaporization over R times 1 over T2 minus 1 over T1. We need to do pressure and torr. You need to do temperature in kelvins. So let's do an example. What is the vapor pressure of benzene? That's 373.2 kelvins. Given is that the delta H of vaporization is 30.8 kilojoules per mole. And the normal boiling point is 53.2 kelvins, and we're at 1 atmosphere, which is equal to 760 torrs. All right, so we can just identify various points of information here. So here's our P1. Here is our T1. Luckily, it's already given in kelvins. Nice. Here's our temperature 2. Here is our heat of vaporization, right? So, and this is the heat vaporization. We'll also use that. Great. Okay, so I'm sure by now you know how to sub into equations. So here is a given equation and solve. Okay, so we start off with our equation, and we have ln P2 over P1 equals negative delta H vaporization R times 1 over T2 1 over T1. Now we're going to sub in data. V2 over 60 torrs equals negative 3080 joules per mole. So I converted to joules per mole out of kilojoules. 8.314 joule per Kelvin mole. Now we substitute in our temperatures, over 373.2 Kelvin minus 1 over 353.2 Kelvin, close parentheses, great. And we can simplify. We have P2 over 760 torrs equals negative 3704.6. Negative 1.517 times 10 to the minus 4 Kelvin to the -1. All right, the numbers I get here. So E2 over 760 torrs to the 0.562, and so P2 equals 1.333 torrs. All right, so this undo Ln with e to the x. Remember, e to the x undoes this. Now we solve for P2. And ta-da, there's the answer. The Clapeyron equation allows us to calculate the melting point. Oh, the molar entropy of a transition state equals delta H bar over TRS. This is the entropy at a phase transition. All right. So we have this little phase diagram, pressure versus temperature. The S, liquid, gas, and we're going to have a slope here. M equals delta Y over delta X equals the change in the pressure over the change in the temperature, because it's P versus T. The Clapeyron equation is used for the slope of the line. Between liquid and gas, or any phase boundary. Your choice. We'll do it for liquid and gas. M equals dP over dt of S transition state over delta V transition state equals enthalpy of transition over T delta V transition state. So we could do an example like this. Calc the slope of coexistence curve benzene near 1 atm. Delta H equals 9.95 kilojoules per mole at 278.7 Kelvin, and delta VF equals 10.3 centimeters cubed per mole. 278.7 Kelvin. Oh, scrolled quite a lot. Right. Then we do mass slope equals dp over dt equals delta h bar transition over t delta v. Transition state equals 9950 278.7 Kelvin times 10.3 centimeters cubed mole 3.47. And I'll move this over to the next line. 3.47 joule per Kelvin cubed times centimeters over 1 decimeter cubed. Cubed that. So the conversion issue. 0.08206 dm cubed decimeter cubed atmospheres per mole Kelvin over 8.314 joule per mole Kelvin. Cease. Slope equals 34.2 atm per Kelvin. Then be at the melting point. At the melting point. Of benzene as a function of T. What do we need to do? Take slope equals dt over dp 1 over 84.2 atmosphere per Kelvin equals 0.0292 Kelvin per atmosphere. Right, this is just this number plugged in down there. All right, so then, what have we talked about today? Today we have talked about phase diagrams and phase equilibria between various phases. All right, for solid, liquid, gas, and water, the first things that come to mind when we think about this topic. So we have looked at phase diagrams for water going between solid, liquid, and gas, and discovered that water is unique because it has an unusual slope. We looked at the phase diagrams and identified the various barrier transitions, and also noted that semi-log plots are quite frequent for these kinds of plots, so we got familiar with doing that transition. This is why water is unusual. One more time, ice melts when it is under pressure because of the slope of its phase diagram. So when the pressure is locally increased, we go more into the liquid, whereas most materials would go more into the solid. So then we made a connection to the Gibbs free energy about these things. So we saw that the Gibbs free energy of the solid to liquid, we followed these lines and we noticed that there's a change in the slope, and if we did the phase transition from solid to liquid, that the Gibbs free energy would more rapidly be getting more negative. So this is why we would prefer to undergo the phase transition. We also looked at the chemical potentials of pure substances in two phases. So we saw that we had liquid and a gas in equilibrium, and so some particles may be going up into the gas phase. However, when they go up, must also come back down and go into the liquid. And this is because the chemical potential develops. And following the Gibbs free energy, we worked out the argument that there would be a pressure, a chemical potential, more precisely, but a pressure in colloquial terms, to equalize the number of particles that went into the opposite phase. We also took a look at the Clausius-Clapeyron equation, which has some limitations because it doesn't take into account the delta V for solid liquid and also assumes an ideal gas, but nevertheless, it is useful. So we use this to calculate vapor pressure of benzene. And basically, if you have any of the three variables, delta H vaporization or your pressure and temperature coordinates, any one of those three things missing, you can use the equation to solve for the missing part. Don't forget to use your laws of logarithms to solve that equation. And we can also use it to calculate melting point, which we demonstrated right here for benzene. Alrighty then, thank you so much for joining us. We've had several lectures throughout the day and we are now getting into the evening hours. So thanks so much for having a marathon day of PChem with me, and we may still fit in one or two more lectures later on today. Thanks so much for joining. We'll see you next time. Bye-bye.